Okay, so here's the plan for the rest of the semester. We're going to spend today one more day on matchings. We'll at least talk about Hall's theorem and talk about the next, what would be next in it. We don't have time to go through the rest of this chapter. I want to spend some time going through colorings of graphs. I'm gonna run out. You didn't happen to see, were there maps in the United States?
Yes.
There were.
I'll go get them.
Yeah. Okay. Okay. So I want to go back. To the problems that we're working on page 267 through 269. So are there any questions about matchings, about this idea is crucial. Let me first make it clear that you don't have to have a bipartite graph to be asking it whether you have a matching or not. Okay, so just to be clear, this is not a bipartite graph, and we can still ask for whether there's a matching in this graph. Okay, so a lot of the problems that they talk about in section 7.2 is primarily about bipartite graphs. We're gonna be at least very briefly talking about matchings in non-bipartite graphs. But beginning Thursday, we're going to move on to something completely different. Okay, so I'm going to give you, I'm sure you're all dying to get your own copy of the map of the United States. And I'll put this on canvas, but I thought it would be nice to give you all hold on. Okay, there's a reason I'm giving you a map of the United States. Just don't worry. I'll tell you. I know there's extras. Just enjoy them if you get extras. Okay, so let me first talk about the United States and why I gave you this map. So here's what we're going to be doing next. We're going to be looking at graphs. So let me imagine a graph. I'm just drawing a random graph. There's no method to this, the way I drew it. And what I want to do is I want to partition the vertices. Partition the vertices. What does partition mean? What does that mean? It's not a difficult question. No tricks. What does it mean to partition? Okay, so we're going to find a disjoint number of sets. So partition the vertices into disjoint sets of independent points. Okay, so now let's talk about the United States for a second. Okay, so every state, Michigan only gets one dot. Every state, let's imagine, corresponds to a vertex. And I put two vertices together. Sorry, I join two vertices with an edge if they share a border. Okay, so clearly Hawaii and Alaska, you don't have to worry about Hawaii and Alaska. They can be any color. Okay, one more time. I'm going to put a vertex in every state. And I'm going to put two adjacent if they share a border. So, for example, Montana. Do we know Montana? No, Montana. Montana's this big one. Okay, that's Montana. Okay, Montana shares some of its border with Idaho, with Wyoming, with North Dakota and South Dakota. Okay, so I'm going to assume. So you can. This is Idaho, Wyoming, South Dakota, North Dakota. So if I imagine that Montana is a vertex, it would have an edge to those four states. Okay, and we're going to do that for the whole map. Okay, and throw away. Michigan has two pieces. Just throw away one of the pieces. So, in case you didn't know, Michigan has two pieces. This piece is Michigan, and this piece is Michigan. Okay, and there's actually water, and it sort of floats by itself. Throw away that little piece. The Upper Peninsula, just throw it away. Okay, so again, we're gonna have 48 dots. Don't put a dot in Alaska and Hawaii. That doesn't. They're not adjacent to anybody. Right? They don't share a border with anybody. Okay? Everybody with me at this point? So now what I'm going to do is I'm going to create a graph. So I have 48 vertices, and I'm going to put two vertices together if the states share a border. Okay? So for example, Colorado has an edge between from Colorado to Utah. It doesn't have an edge. There's no edge from Colorado to Arizona. Okay, there's no edge because it doesn't share any border. You can have, there's a point in intersection, but four corners doesn't count. Does everybody know where Colorado is? And the four states are the four corners. Okay, so Colorado is adjacent to Utah, New Mexico, let's see, Oklahoma, Nebraska, this one and that one. Iowa, and Wyoming. I'm not good at geography, you know. Okay, so Colorado is adjacent to a lot of people, a lot of states. Okay, so I get a graph. Vertices correspond to the states. Edges correspond to if they share a border. And notice it doesn't have to be a big border. So like for Colorado, it shares a very little border with Oklahoma, but it does share some border. Okay, so there's an edge between Oklahoma and Colorado. Okay? Now I want to color the vertices. You're not going to do this right now, but this is the goal. Color the vertices so that adjacent states get different colors. Okay, now before you start, before the comedian comes out and I'll be the comedian. Yes, you can do it with 48 colors. Okay, so if I give every state a different color, then certainly no two states of the same color share a border. So as mathematicians or as scientists, what do you think we would want to do? Let me make it even better. As a map colorer that has to have a color for each different color, one of these for each different color, what do you think you want to do to make it as easy as possible? Minimum number of colors. Okay. And again, I may have mentioned this back in the 16th, 17th, 15th, 16th, 17th, and 18th century, map makers changing colors in the map making process was expensive. So this was an important problem back then. It's an important problem now for many reasons, but it really had relationship to maps. I won't give you the answer. For non-turning in homework, see how many colors do you need? Okay, what's the fewest number of colors to color the map? Don't do it now. Just that's for homework. But that's where we're going to. That's where we're headed. So now let me give you the graph version of this. Forget the map. Forget the map of the United States. Let's give me a graph. Color the vertices. With as few colors as possible. Okay, color as few colors as possible with adjacent vertices getting different colors. Now, if we just left it like this, then in fact, the problem is not as interesting, and that's why I gave you this map. It's not as interesting as it could be, because let's just let me take K5. How many colors do you need? Let's just choose any two vertices. They're adjacent, so they have to.
You need 5 colors?
I need 5 colors. Okay, so the problem, I need to be more interesting. I need a little bit more information, and in fact, finding the largest complete graph in a graph often gives us this minimum number of colors. So what I want to do is look at a special class of graphs. A special class of graphs that corresponds to not the United States in general, but maps. Okay? So I'm going to call a graph planar. Planar if the graph can be drawn in the plane without crossing edges. Okay, so that's what I mean by planar. Planar. This is a plane. Okay, plane can be as big as you want. Okay, so first thing I want you to look at is, can you draw K5 in the plane without crossing edges? obviously, let me just make it clear. This clearly has crossing edges. Right, you see the edges that cross. But, maybe I don't need that one over there. I'll just put that one over here. And maybe I don't need this one here. I'll just put this one here. Well, I'm so close.
Does it have to keep the same shape? Because if you put it out and
You can, it's just 5 vertices anywhere you want, and you want to make each pair adjacent, and you don't want their edges to intersect, cross. So, for example, if I drew it like this, then there are 3 edges. Okay. So that's I want you to think about that for Thursday. So, I'm so close. There's just one pair of crossing edges. One pair of crossing edges. Okay, so you're going to think about that. And the other one I want you to think about, at least in the plane, K33. Can you draw K33 in the plane without edges crossing? Let's imagine. Here's. I don't have to draw it like that. I can put the points, the vertices anywhere I want. So. And now I just have one more vertex, like here. My problem is going from this vertex to that vertex. Okay, so think about that. And on Thursday, we'll come back and talk about these 2 graphs and the interesting fact about these 2 graphs. I'm going to give you one more problem to work on. Now let's suppose that we don't live on Earth. We live on donut. Okay, so planet donut. Okay, there's planet donut. Planet donut. And I'm going to draw things on planet donut. Like, can you draw K5? Can you draw K5 on planet donut? So remember, what's interesting about planet donut is I can go the edge can go like this. It can go up here and then go around the back. It's on the back of the donut and come over. So it's on the back of the donut and then come over and then come back over here. You might want to buy a donut for this, or a bagel. Okay, so it doesn't. There's the bottom of the donut. There's the bottom. Can you draw K5 on the donut without having any of the edges cross? Okay. So that's. If you give up on this, and I'm not saying you should give up, because probably you could do it. Can you put it on the donut? Okay. And if you give up on K33, can you do it on the donut? Okay, and that's That's where we'll start on the last 2.5 weeks. We'll be talking about these sorts of problems moving forward. Okay, questions? Okay, and that's just to give you an idea. That starts on page. We're going to skip a bunch. So if you look at page 309. Or you don't have to look at 309. 309 is where we're going to start. So vertex colorings and planar graphs. What do you think it means to be a planar graph? What do you think it means to be a planar graph? What do you think? Planar? Okay, so you can draw the graph on the surface, on the plane, without any crossing edges. By the way, how about K4? Can you draw K4 on the plane? I mean, so here's K4. This is the way I always draw K4. Can you draw it in a way where none of the edges are crossing?
Yes.
Yeah, how would that be? There we go. Okay. So simply either go like this, or I just always like this one. Those are the same. They look different, but they're the same. And let's see, K33. We're going to have to decide whether we can draw that in the plane. But what about K23? K23. So just to remind you, here's K23. Can you draw that without any crossing edges? It's good when you're going like this. What does that mean? Okay, so you want me to do this? But I'm so close. One more vertex, and there's got to be a way. Maybe this edge. Maybe I want to draw that edge somewhere else. But can we get K33? This is not K33. This is K33. Okay, so that's where we'll start on Thursday. So to continue with, I gave you several problems to look at, and I want to go back to page 267. The bottom of 267. So number 7, did everybody get the teachers and classes? Number 6? Okay. Number 5, I think we did number 5. Mm-hmm. Number 6. 6, can the teachers with this arrangement teach all the classes?
Yes.
Yeah. Okay, and it corresponds to a matching. Okay. So what about 7.29? Or, sorry, number 7. Is BXCY a matching? So let's make sure. A matching just means a set of edges which do not intersect. Do not intersect vertices. Now I just worry about vertices at this point. Okay, so one more time. BXCY, that looks like a matching. What about AX, BY, CY? So part B. No, why? Y has two edges to it. Okay, so that's no. What about AX, BY, CZ? Be careful. AX, BY, CZ. Okay, that looks, is that a matching? Mm-hmm. Yep. Is AX, BW, CZ, DY a matching? I'll assume each of those are edges. Okay, one more time. AX, BW, CZ, DY. It is a matching.
Yes.
And it's a perfect matching. If it's a matching and contains all the vertices. Okay, so that's the definition of a perfect matching. It is a matching, so it's a set of non-intersecting, when I say non-intersecting, they don't share any vertices. So non-intersecting edges that contain all the vertices. That would be a perfect matching. So the first thing, can you give me a criteria? I'm going to give you a graph, G. Can you give me some criteria that automatically tells me there's no perfect matching? You don't even need to know what the graph is. So some of the edges have a repeated vertex.
Well, let's just say CX and DX are both in your matching.
Yeah, but no. I have a graph, and I want a condition that absolutely tells me there's no perfect matching.
I'm sorry, I thought the question was not a matching.
So I want a perfect matching. What about a condition? It's maybe just an isolated vertex would be bad, but even better than an isolated vertex. What can you tell me about the number of vertices? Do what? Which one was good or which one is bad? Odd is bad. If I have a graph with an odd number of vertices, then there's no way to get a perfect matching. Okay. Hopefully that's clear. Okay, so we need to be sure that we have an even number of vertices when I'm looking for matchings. We ended with finding the number of perfect matchings in CN. I think I was standing over there. Number of perfect matchings in CN. And again, perfect means it contains all the vertices. What'd you just tell me? I have no perfect matchings if what? N is odd. Okay, no perfect matchings. Okay, what about if N is even? So let's take the smallest even cycle. There's 2 in C4. Two in C4, right? The vertical ones and the horizontal ones. What about C5? There's none. What about C6? 3? What would that be? Let's see, C6. So let's actually go through a proof of what the answer is. Let's look at this edge right here. If that edge is in a perfect matching, can this edge be in the perfect matching? Can this edge be in the perfect matching? And how many edges must you have in a perfect matching? 3. So look, if I don't have this edge in the perfect matching, then this vertex we're not covering it. So this edge needs to be in the perfect matching, and this edge needs to be perfect. So there's one. Is there another one? That's it? Ah, okay. Okay. So C6 has 2. Don't let me fool you. What about C8? 2? You sure? Okay. Everybody sees 2 perfect matchings in C8. C10? C14? C17? Okay, very good. 0. Okay, it's got to be even. All right. Okay, that was problem number, which one was that? That was problem number 8. And what about K and N? Let's start with, did we do these last week? Did we do these? We did them, it was a while ago. Say K33. 6. Who said 6? Why do you know 6? What? Why is it 3 factorial here?
Because for the first one, it has 3 points.
Very good. Okay, so I'll choose this point. There are 3 possible edges.
Yeah.
Okay? Whenever I choose, you choose any one of them, and what graph is left?
K22.
Very good. Okay. So I choose any one of them. K22 is left. And how many, we know how many there are. So it's 3 times 2 times 1, but 3 times 2 is 3 factorial. Okay? What about K? What about K and N? Okay, so K and N, there are n factorial perfect matchings. And what about Kn? Kn. Kn is the complete graph. Oh, wait, okay, so n times, let's see, so n times n minus 2, n minus 4. First of all, we know that n has to be even, right? Okay, so n times n minus 2 times n minus 4, down to 4, 2, and then that's it. Okay, we choose any one of the n edges. Let's draw Knn. Here's the point x. It could be this edge, or it could be this edge, or it could be this edge. So there are n possibilities for the edge matching up x. When I remove this edge, what's left? So let's say I'm including that edge. This is Knn. Oh, sorry. Sorry. I guess we've already done this. Okay, Kn. So what do you mean? So I have Kn. I choose this edge. How many ways could I choose an edge from the vertex x? N minus 1. Okay, so I'm going to start with n minus 1. And once I remove this edge, what's left? 2n minus 2? Right, n minus 2. Okay, one more time. We need to take the complete graph on an even number of vertices. Okay, so let's take K2n. So there are 2n minus 1 ways to choose the first edge. 2n minus 1 ways to choose the first edge. Then I'm left with K2n minus 2. How many ways can you choose an edge here? let's just imagine I started with this edge right here. How many ways can I choose an edge to pair up with this vertex? 2n minus 3. And then the next one, 2n minus 5. Down to 3, down to 1. Okay, so this would be when I have K4, there's 3 ways to do it, and when I have K2, there's only 1 way to choose. Okay, moving down in 2s each time. And well, we could, I'm not going to, just out of curiosity, how many of you are going to be here in the fall? Be in school in Denver in the fall? Anybody thinking about taking combinatorics? Well, that's going to be, we may or may not have a class. Okay, all right, so I was going to say this can be written as, I can rewrite this, I'm just going to write it anyway. I can rewrite this as 2n factorial. And what am I dividing out by? I'm dividing out by all the even numbers. All n even numbers. So I need 2 to the n times n factorial. So notice on the bottom, n factorial times 2 to the n means that I have 2n, 2n minus 2, 2n minus 4, down to 2. The bottom is all of the even numbers. And what's missing from this product? Someone say all the even numbers. All the even numbers, thank you. Okay. So if you take combinatorics, if this encouraged you enough to say, hey, that's pretty interesting, we're looking for people to take that class. So that's we'll be doing a lot of counting in combinatorics, which is what combinatorics is all about. Okay.
What's the thing up here where it's n times n minus 2 times n minus 4? Did that correspond to something?
So what did that correspond to?
That's what I'm trying to figure out.
So what did n times n minus 2 times n minus 4, what did that correspond to? KNN. The number of matchings in KNN.
That wasn't n factorial?
That was, well, that's this. Okay, so one more time. Sorry. This up here, here's KN. Okay, what did this correspond to? Sorry, this is the number of perfect matchings in KN, where n is even.
Okay.
Okay. Yeah.
Gotcha.
Right, because I have n choices, I choose a vertex, I have n choices, then I choose another vertex, there's only n minus 2 choices, and so forth. Okay?
Oh, I see. The thing below is K2.
K2, yeah.
Okay,
Right.
Gotcha. Cool, thanks.
Okay. So just to sort of finish this out, number 12, this is a famous problem. I like to think of this rather than, there aren't too many games that get played on a 6x6 board, but there are games that get played on an 8x8 board, like chess, right? So you know how a chessboard looks like. It's also easier to divide it up, right? We just keep dividing in half. So what can you tell me about an 8x8 board? What can you tell me about a chessboard? What's kind of unique about that? Chess, checkers, 2 colors, always 2 colors, right? Notice this board doesn't have any colors. It's hard to see that. So let's see, blue, white, right? I haven't seen too many chessboards that are blue and white, but anyway. So if this one's, so this one is this. how many squares? 64. What I'm going to do is I'm going to cut out opposite corners of the chessboard. Okay, I cut out opposite corners. So now I've gone from 64 squares to how many squares? 62 squares. And now I'm going to give you 31 dominoes. 31 dominoes. Okay, so a domino covers exactly 2 squares. And the question is, if I give you 31 dominoes and I cut out the opposite corners of the checkerboard, can you cover the checkerboard with 31 dominoes? Okay, one more time. I'm going to cut out opposite corners, and I've really given it to you, but the answer is here. I'm going to cut out opposite corners, very similar to the problem in the book. But this is 8 by 8. So I have 64 squares. I cut out 2. I have 62 squares. I give you 31 dominoes. Each domino covers exactly 2 squares. Can you cover the board with the 31 dominoes? You know the answer. You can't say it. You took combinatorics. Okay, when I cut out opposite corners, how many blacks, before I cut out opposite corners, how many blacks do I have, and how many blues do I have, and how many whites do I have? 64. I have 64 squares. How many are black and how many are white? Do what? 32.
No, 34 white and 30 black? Or 33 black and 33 black.
No. Before I cut out the opposite corners, we have how many whites and how many blacks? 32 and 32. Is that right? Now, what's amazing about opposite corners is, what's the color of this one? What's the color of this one that I took out? Blue. And what's the color of this one? So now what do I have left? I have 32 whites and 30 blues. What does a domino cover?
1 white and 1.
1 white, 1 blue. So is there any way to cover all 62 spots with 31 dominoes? No. Because each domino covers a white and a black. Okay? That's not so amazing. Okay, so I'm going to go back just for the heck of it. Here's a problem I want you to think about. This is a weekend problem. So this weekend. Okay, I'm back at an 8 by 8 checkerboard with 32 blues, these are blues, and 32 whites. Okay? Now you have a machine, you can take any of the squares and cut them out. So hopefully you see that if I cut out 2 blues, I'm in trouble. And if I cut out 2 whites, I'm in trouble. When I say trouble, I'm going to give you 31 dominoes to cover. Okay? Cut out any blue and any white. So I'm going to cut out 1 blue and 1 white anywhere. So I could cut out this blue one and this white one. Or this blue one and this white one. Okay? So again, I have a checkerboard, it's all colored. I'm going to cut out one blue and one white. So when I cut out one blue and one white, how many blues do I have left? 31. How many, when I cut out one white, how many whites do I have left? 31. I give you 31 dominoes, cover the board. Okay, that's when you have some time to kill, that's a fun problem to play with. So that sort of takes us through problem number 12. Sorry. I still didn't do the problem that I really wanted to. I'm going to go back to number 7 for a second. Because I like the counting part of number 7. The counting part of number 7. Unfortunately, it's on the next page, so I keep forgetting about it. So number 7, I have this graph. I have this graph on number 7. And the question is there a perfect matching? That's not hard, but is there a perfect matching? Yes. Just one that comes to mind immediately is AW, BX, CY, DZ. Okay? I want to jump to VI, 6. Find the number of perfect matchings in G. Okay, so let me see if I can draw this. That's the graph. How many different perfect matchings are there? 4. How'd you get 4?
This is like for the leftward vertices, you have 2 ways to.
Okay, for these 4 vertices, there are 2 ways to match these 4 vertices up.
And for the right one, there's 2.
2 ways to match these vertices up, and 2 ways. But you have this edge.
But if you have that edge on your perfect matching, the right top 2 vertices doesn't have any.
Very good. Okay, so this edge is in no perfect matchings. Okay, is that clear that this edge can't be in any perfect matchings? Because if this edge were in a perfect matching, then what's left over here looks like this. And I would have to match those 3 vertices up. And what's left over here looks like this. Okay, so this edge is in no perfect matching, so it's the number of perfect matchings in K22 times the number of perfect matchings in K22, and we know that this is 2 times 2. Okay, very good. Okay. All right, so let's see. Finally, what about number 13? So it's a 3 regular graph, again called the triple fly swatter, just fly swat. It does not have a perfect matching. But it does have a matching with 7 edges. Okay, so again, it's 3 regular. By the way, how many vertices does it have? The first thing you should ask, if I'm trying to find a perfect matching, what's the one condition that you absolutely have to have to have a perfect matching? Number of vertices what? Even number of vertices. Good. It's got 6. Oh, I didn't finish it, did I? I want to give you as many edges as possible. So this has 16 vertices. If it was to have a perfect matching, that would mean a matching of 8 edges. Why can't it have a matching of 8 edges? By the way, it doesn't have a matching of 7 edges. Can you find a matching of 7 edges? Okay. Can you show me where?
So the two first boxes on the bottom, and then choose one of the edges that's connected to the middle.
So just to, I'll take these two. I'll take these two. I'll take these two, and then I'll take this one. So there are 7 edges. It's a matching with 7 edges in it. I'm so close. Can't you find one with 8? This is usually a time when I ask you to vote, but I think the vote will be obvious. The question is, can you prove that it can't have 8? Which is what the book asks. Okay, so one of the things I want you to understand, I've been pretty easy on looking for detail on proofs. On the final, there's going to be a couple of proofs. And one of the things that I would like you to think about is, how do I write up a proof with all the detail? Okay, so let's think about, how would I write up a proof that there's no perfect matching in this graph? So I'm going to start. Suppose there is a perfect matching. So I'm going to prove it by contradiction. Suppose there is a perfect matching. If there was a perfect matching, and I'm not writing these words down because I'm running out of time. If there is a perfect matching, then X gets matched up with some vertex in one of these pieces. What's left? Take that green edge out. What's left? Take this, the green edge and the vertices out. One more time. If there's a perfect matching, X is matched up with something. And without loss of generality, I can assume that X is matched up with this one. It's the same if it was matched up with this one, and it's the same as matched up with this one. Is that clear? Okay. So let's imagine that X is matched up without loss of generality. X is matched up with this vertex here. What's the problem? No. What do you mean no edge?
Between those remaining two.
More. Okay, so when I remove this vertex, what's left? What's left in this graph when I use this edge as part of the matching? What's left?
These two vertices are left.
Well, that's because but more important is, there's two pieces, two isolated pieces that have 5 vertices, that have an odd number of vertices. Okay, and there certainly is no way to find a perfect matching in a graph that has an odd number of vertices. Okay. So now you would have to write that in detail if I give you this proof on the final exam. Hint. It won't be that easy. Okay. All right. So I didn't get to prove. We didn't get to Hall's theorem. So what remains in the rest of this chapter is so what conditions give us a perfect matching? What conditions in particular? What conditions? By the way, does everybody understand the problem I gave you on this? Okay, so one more time. Choose a black anywhere. So I'm in green. So I shouldn't make this green. This is not green either. Okay, so I choose a black square and a white square. I need to make sure I have a white square. So this is a white square. This is a white square. So take those two squares out. Cut them out. You have a saw, a little jigsaw. You cut this square out and you cut this square out. And I believe those are different color squares. I believe that's the case. Let me make sure. Do I believe that? Do I believe that? That's not right. So black, white, black, white, black, white, black, white. So let's make it this one. One more. White, black, white, black, white, black, white. Yes. Okay. So I cut those two squares out. When I cut those two squares out, I have 62 squares left. Now, what you might want to think about is, what is the bipartite graph? This gives us a bipartite graph with 31 vertices on each side. So there are 31 black ones and 31 white ones left. And you want to find a matching in that bipartite graph. And in fact, there's a very nice application of Hall's theorem, of the theorem in section 7.3 and 7.4 that actually might help us find that perfect matching. Okay. So Hall's theorem gives us a condition on when there is a matching. If I take in a bipartite graph. So if I take a bipartite graph, and it's not a complete bipartite graph. So here's X, here's Y, it's bipartite, and there are some edges between there. We have some edges. Hall gave us a very nice condition, essentially the most obvious condition. If I close my eyes and I choose any subset of X, then if there's going to be a matching, how big should the number of vertices be adjacent to this, let's call this A. So A is adjacent to some, A as a set is adjacent to some points in Y. If there's any hope of having a matching, what can you tell me about this set right here? Do what? Same size? Does it have to be exactly the same size?
If it's
Do what? Or bigger. So if this is, let's call this B, if the order of B is greater than or equal to the order of A, then we have a chance. Well, let me say what I mean by that. If in fact here's a set C and here's a set D that is visibly smaller than C, visibly, then there's no way to match up the vertices in C with the vertices in D. So the obvious condition is that the number of vertices adjacent to A in Y is at least as big as A. And that's, if that's true for every subset in X, then there's a matching. Then there's a matching of all of X. And this was proved in the 20s by Philip Hall. And it was sort of groundbreaking in terms of finding a matching. Matchings in bipartite graphs turns out to be a very important application in a lot of the problems that occur as applications. So we're looking for this matching. Now, we went a little bit further. What if we don't have a bipartite graph? We can ask for a matching in a graph that's not bipartite. There's no reason why we can't. And there aren't as nice conditions that give us when there is or isn't a matching in a graph in general. But certainly we can ask for perfect matchings. Like K6, we know has a perfect matching. So it doesn't have to be just bipartite. But Hall's result gives us a very nice necessary and sufficient condition for there to be a perfect matching in a bipartite graph with equal sets and a matching of all of x if y is bigger than x. Okay? So we're going to skip over that, but that's essentially section 7.3, and then again we're going to move on to I'll get there. Page. I guess that's where the maps are. So I'm going to move on to page 309, chapter 8 for the last 2.5 weeks, and we only have 2.5 weeks left. Okay, so we're going to start with chapter 8, and that has to have. Oh, look, the picture on figure 8.1.1. Imagine that's not in the United States, but imagine it is the United States. The question on 8.1.1 was, can you color these, I don't know, however many states there are in that map? Can you color it with different colors so that each region that shares a border is colored a different color? And I'm colorblind. I have no idea. 4 different colors?
Yes.
Is that 4 different colors? Yes, 4 different colors. Yes. Oh, it's in color in the book. It's in color. Mine's not in color. Okay, so that's a theorem that took a very long time to prove, and I think we've talked about it, or you may have heard about it, that it took about 200 years to prove it, and originally it was proved by computer. And if you ever hear the story of the 4-color theorem, it was proved by 2 mathematicians at the University of Illinois, and it was done in 1976 on a computer. So if you can imagine, apparently they had piles of output, paper output. Computers couldn't store a whole lot of stuff back then. So, but that proof has been checked, and it is true. If we have a graph that can be drawn like countries, and we'll talk about what that means, then in fact we can color it with 4 colors. Okay? All right. So the papers were graded, let's say, leniently. I think that would be a good description. The proofs, you still need some work on the proofs. And I would like you to at least, if you didn't get number 4 right, you should work on number 4, because it's a pretty simple proof, and I might think that you might see that again. Hint. Okay, and hold on. Yuting Song? Is it Yuting? V is not here. Yuyan Gao? Ben? Selma? Jianwei Wang? John Wei Lu? Jiwen Mao? Yeah, they come only for the test. Xinyi Shan? Xinyi Shan? She's also not here. Xijia Lu? Allison is not here. Sarah is here. Sarah?
Thank you for trial and error.
Connor? Vicky?
Well, hold on, but this is,
Rui?
we got 2 to the N over 2, and over there we have 2 to the N.
Yang Chen? Ying? Pam? Wendy? Leslie? Jinyan Liu? Is that you? Oh, hey, I have another one. John Wen Lu. These are homeworks. Old homeworks. Wendy, Leslie, Allison, Pam. We'll see you Thursday. Or Monday, whatever day. Wendy, Leslie, Allison. Does everybody have their paper? I didn't think so.
修持上。
Oh, there we go. So, how do you say the first name?
秋实。秋实。
Chu Shan.
Yeah.
Okay.
Thank you.
I'll work on it.
千惠 starts with a T.
Yeah. That I figured that one out.
Thank you.
Anybody else? See you Thursday.